Okay.
All right. So again, we have a little bit technical difficulty in the classroom here. If I turn off the light, it may become dark. So we have to just go with that for now, and I'll turn the lights back on after we are done speaking here. I think, are you able to see some of our distance students? They joined online.
I am.
Okay. So I'm going to set to the speaker view here. Maybe. Perfect. Okay. I think it's about time. Good morning, everyone. As I already mentioned about Mr. Ken Elschlager, and we used some of his materials in the first few classes. But today we have Ken is going to talk to you about the blast-induced effects and how to control the blast-induced effects, ground vibrations, air loss, and etc. So it is now my pleasure to introduce Mr. Ken Elschlager. Ken is a mining engineer with the Office of Surface Mining Reclamation and Enforcement, OSMRE, used to be OSM, Office of Surface Mining. So he has worked on coal mining, blasting related issues since 1985, as I mentioned, when we were discussing about the public relations, and I got the PowerPoint presentation from Ken, and we have seen him already in the slides. So he provides technical assistance and advice to the states, investigates citizen complaints, and evaluates the adverse effects of blasting on people and property. He's an instructor for OSM technical training classes on blasting, mine gases, public relations, instruction techniques, underground mine technology, GPS, and Excel. As the OSM Blast Certificate Coordinator, Ken administers the OSM Blaster Certificate Program and helps the states and federal agencies to conduct blaster certification and continuing education training. Ken is a past director of the International Society of Explosives Engineers, ISCE, and has chaired the blast vibration and seismograph sections and public education and public relations committees. He is the current chair of the ISCE Standards Committee. So with that, please welcome Ken Elschlager. And Ken, the floor is yours.
Thank you, PT. Well, good morning, everyone. Hope you're all staying warm out there in South Dakota. We're waiting for your cold air to get to us in Pittsburgh here. Probably won't be as cold, but nonetheless, we'll get a bit of it. Well, I'm happy to be here today to talk a little bit about the adverse effects of blasting and what the blasters can do to minimize those effects, which ultimately result in complaints, and certainly the more we can reduce those types of things, the better off we all are. Before I get started going down that path, I just want to give you a little background on OSM. As I said, I'm here in Pittsburgh. There's my contact information. And OSM is a regulatory agency on coal mining. As you see in our emblem, they've got a little scales of justice there, trees on one side, coal on the other. Our job is to balance the energy needs of the country versus the environmental needs and productivity of the land. So we try to be relatively balanced in our approaches. We regulate active coal mining in a wide variety of different areas. One of them is blasting, where I am the blasting certificate coordinator, issue licenses to blasters, and I also coordinate those activities with all the states across the board. In addition to that, as PT said, I look at things that have gone wrong in mine sites from a blasting standpoint, look at it from a forensic engineering standpoint, root cause analysis type of things. And that's hopefully what I'm going to be able to share with you a little bit today through a number of videos, and then those things that the blasters are going to be able to do to help avoid the things that we see. Other things that OSM does, we are not the frontline regulators. We pass our responsibility on to the states and pay them to do that from a 50% standpoint. So I'm not a frontline person. I'm normally second line. I'm a technical consultant fundamentally to the states. That's where I perform most of my activities. Then the other thing that we do is we affix abandoned mine land problems from those mines that were vacated or left abandoned prior to 1977. Sometimes we do blasting for high wall reduction there, or maybe to dig trenches to isolate mine fires that are burning underground, but very little blasting on that side of our program. So those are our two primary items, active mines and abandoned mines, just to give you some idea of what I do. Where does OSM work? Where can we be found? Any of those places on this map where there is coal mining, and the colored schemes represent areas of coal mining in the states that we can be found in. We're in 34 states, or there's 34 states that mine coal. The other 16 have no coal in their boundary, so you won't find us there. Production-wise, I'm sure all of you are keenly aware of this. For many years, West Virginia, Wyoming, West Virginia, and Kentucky have been the top of the production scheme. If you look to the far right, 2019, that has changed. Kentucky has dropped to number 5. Illinois and Pennsylvania has overtaken them in terms of production. The reason I bring this up is because it also reflects where most of the explosives in this country are used. About 70% of the explosives on an annual basis are used at coal mines. Hence, the number 1 and 2 consumers of explosives at this point in time are going to be Wyoming and West Virginia. A few years back, Kentucky would be 3rd. All right. So there's a lot of explosives used at coal mines. The good news is it's mostly in remote areas. So that being the case, it's a lot easier to control the adverse effects when you're not on somebody else's doorstep. So it's also a good place for new blasters to cut their teeth because they're in relatively isolated environments. And they can do that quite well. All right, so, controlling the adverse effects, you probably talked about ground vibrations, air blast, fly rock, fumes, dust up until this point in time. But I throw this slide up here to illustrate the wide variety of things that one can encounter in a blasting environment. This is a railroad recut. They're eliminating the tunnel in the center part of this photograph. It's a single track tunnel. They wanted to make it a double track. So they decided to excavate the hillside down. Well, a lot of constraints here. Had to keep the tunnel open, had to keep it operational, couldn't interrupt train flow during this operation. As you can see, they're getting pretty close. Fortunately, there's not many houses near here, but these rocks down in the stream were a very popular place for people to swim and just sort of hang out. This bridge here represents the Great Allegheny Passage between Washington, D.C. and Pittsburgh. It's a bike trail that goes through a tunnel right behind this cut. So not only did they have to be aware of the bicyclists here, but also the stability of the tunnel going through the back part of this cut here. Huge amount of controls, but the products are there. The people with the right knowledge are able to successfully eliminate the adverse effects and perform well on the blasting front. And they conducted this project with no incidences and no interruption of train traffic through this tunnel. So it's a great example of how tight things can be, but again, you can do very challenging projects with the right know-how and the right explosive products. A couple terms I want to talk about before we get going so you understand what I'm talking about. Okay, normally from a blast site standpoint, I'm going to be referring to the perimeter of the blast holes plus 50 feet That's fundamentally the area that the explosives have the potential to impact when they're detonated. That's the intended rock breakage area. The blast area or permit area is the same as the work area. It's the area in which none of the material from the mine is allowed to go beyond that area, and most importantly, from a fly rock standpoint. The blast area is that area defined by the blaster where he thinks there's a possibility of people getting injured as a result of one of the adverse effects of blasting. What are the adverse effects that can injure somebody? Concussion or air blast, fly rock, or any other type of flying debris, and fumes. So the blaster is responsible for defining and securing an area large enough so that some type of injury cannot occur. Now that area is not limited to the permit area or the construction site area if you're looking at construction projects. All right, so we can extend beyond that area if needed to ensure protection of the public. Now in this instance, that blast area encompasses a house. Can they force the people to leave there? No. All right, so it's not wise to extend the blast area into somebody's house. If they agree to leave, maybe it works, but they have no obligation to do that. So it's a risky thing. So really blasters need to be concerned with designing blasts in such a way that any of the adverse impacts are limited to the mine site. Okay, so a very important concept, to understand. And it's a blaster's responsibility to define this area. They will generally enlist the assistance of mine management and other people to secure those areas. They're by and large focusing on detonate the blast in a safe fashion and make sure that it performs well. So there's a number of people come in to play to make sure that people are protected and there are not significant adverse effects. It's team effort, just that simple. All right, so here's the adverse effects that we're going to talk about. I'm first going to talk about ground vibrations and air blast, then we'll talk about fly rock. Fumes is a little tougher to talk about. I'll briefly touch on that. Okay. First off, just a couple things about blasting basics. I'm sure you've covered this. It's sort of a review, but there's two things that significantly affect the generation of adverse effects. And one is going to be the size of the charge, and the other is going to be how deep it's buried. So those two together are going to define the confinement of the explosives in the ground. And in this small graphic, which is out of the Atlas book, Explosives and Blasting, it represents the same size charge detonated to one on the left, detonate pretty deep in the ground. There's no reflection or effect on the surface. All that energy is going to be confined in the ground, and it's going to create a lot of ground vibration. On the right-hand side, the charge is buried very near the surface, if not on the surface. Going to be a large amount of flying debris and a lot of air overpressure that's generated. What's the blaster trying to do? They're looking at item B and C, these two items here that relate to basically burying the explosive just the right depth so that you get the fragmentation necessary so that the machinery on site can excavate the rock. All right. So charge size and confinement as a general rule are very important concepts in terms of controlling the vibrations. Strong influence, direct influence one on the other. From a blast design standpoint, again, you've had this. There's going to be a series of holes as laid out on the right. I've got a pattern that is 4 rows deep, 5 holes per row. and each one of those holes are going to be loaded in some fashion as indicated here on the left-hand side. The red portion of the hole is the main explosive charge. In most mining applications, it's going to be an ANFO emulsion or an ANFO emulsion mix. It's going to be confined in the ground with stemming at the top. There needs to be enough stemming on top of the hole so that the energy doesn't rifle out the top. The primers, which is a combination of high explosive and detonator, going to be located in the bottom of the hole. This is called indirect priming. They generally prime in the bottom for the purposes of starting this detonation at the bottom, and the energy is focused laterally towards, say, this high wall right here. As it moves up the column, it bellies this high wall out and fractures the rock. Direct priming would put this primer at the top, very infrequent, because that causes the top of the hole to have a stronger potential to rifle. So bottom priming, indirect priming, is a primary way to control where the energy is focused. And we certainly want it to be focused on the burden or the rock mass in front of the hole, that vertical high wall in front of the hole. And that all relates to powder factor. There's going to be, generally speaking, a certain number of pounds of explosive per cubic yard of material, and that's going to vary depending on the hardness of the rock. The weaker rocks, shales, are going to require a lower powder factor. Sandstone's a little bit higher. Limestones, dolomites, granites and other things are going to require much higher powder factors for successful breakage. It's all about finding the right product, the right burden and spacing for the rock type that's there to have the shot perform well, not only from a fracturing standpoint, but also from an adverse effects control standpoint. All right, so what are the key important things? You've talked about distances and using distances to calculate allowable charge weight per delays based on scale distance. All right, those are the primary things. Okay, we're going to touch a little bit on spatial relationships. And obviously, I've just spent a lot of time talking about confinement, because the size of the charge and the depth at which it is buried defines the confinement and strongly affects the generation of adverse effects. All right, so a couple examples. Heavy confinement, right about in here. This is a seismic charge. You're going to see it detonate. There's fundamentally no expression on the ground. Here it comes right now. Boom. Probably a kilogram charge. Sometimes they use 2 kilograms, which is 4.4 pounds, but there's generally no expression on the surface. All that energy is confined in the ground, meant for picking that up on seismology instrumentation that has been deployed in the field for the purpose of defining mineral reserves underground or oil and gas reserves. But they're, again, heavily confined at that point in time. All right. All right. A strong construction type blast.
Okay, cameras on.
Some of these blasts occur in very close proximity to homes. So a longer video, but it illustrates the fact that you've got a warning signal. The blaster has cleared the area. And obviously it's going to be pretty well confined. There's going to be a bit of heaving, but there's nothing radical. That's the way those shots need to be deployed in the field to protect the nearby properties. In this instance, they kept all the material on site. That would have created a little higher ground vibrations by virtue of its confinement than your standard coal mine shot. But the air blast and fly rock were significantly reduced. In a moment here, the guy's going to walk on site and it'll give you some idea the size of this shot. It wasn't very big. All right, but when you're close to structures, you need to keep the shot small so that you can ensure successful performance. All right, from a mining standpoint, here's a shot that's relatively well confined as well. Heavily confined. Material barely moved. It's going to create very strong ground vibrations, but no air blast, no fly rock. Very well controlled. All right, here's an optimum coal mine shot. A little bit more heave there. As you can see, there's a bit of fumes that come up from that, and it's up to the blaster to continue to secure the area until we can clear the blast of not only undetonated explosives, but make sure that all the fumes have dissipated. In that particular instance, fumes dissipated very quickly. Wasn't much concern with it drifting off site into the woods behind the shot there. Fortunately, in this instance, there's not a house back in that direction. But, you know, my part of the world, this is hunting season, and there could be somebody back there hunting. So you got to be careful when fumes are generated and they wander back into the woods, because there could be somebody back there unless the blaster took active measures to clear that area. So just words of warning. All right, here's a high wall shot. Casting shot, very well controlled, very little fly rock, all the material moved laterally. These types of blasts from an adverse effect standpoint generally create pretty strong ground vibrations as well as pretty strong air blast, because that face, that free face up front that is pushed out rapidly in front acts like a huge piston. And it creates a very low frequency pulse that can travel quite some distance. In a remote area like this, not a concern, but certainly an activity that one would probably just keep away from if there were houses nearby. But there again, it's a very well designed, very well controlled blast. And also, this type of activity takes a huge amount of effort in the field to make sure it's conducted properly. From a drilling standpoint, from a loading standpoint, got to try to avoid drilling crooked holes. The drillers are very important people in successful performance of these types of shots. The blasters that are loading the holes, a little bit too much, a little bit too little, and things can go wrong pretty quickly. So it's a team effort again. Here's one of marginal effort. Whether that was design related or field implementation related, I really can't tell you. I don't have the details, but it's certainly a lot of energy that's wasted into the atmosphere by virtue of throwing rocks and or creating a lot of holes that blow out the top. I would prefer to have that energy expended breaking the rock mass or moving the high wall toward the spoil side. Here's one that throws rocks significantly. Fortunately, the camera was on the tripod. In my mind, there's no reason ever that a shot performs like that for any reason. That's simply bad design. That is bad drilling, possibly bad loading, or a number of things. Okay, but these are things that the engineers and the blasters need to work together on to make sure that there's not significant throw, elevated air blast, or elevated ground vibrations. This takes you to the disposal range. This is on an ATF range that I taught a class at a number of years ago. They're going to do a couple open air detonations. First one was 25 pounds Unimax. At 1,000 feet, I got an air blast reading of 144. That as well was 25 pounds of Unimax separated by 500 millisecond delay caps. The air blast was significantly reduced down to about 139, almost a twofold reduction in air pressure at 1,000 feet. Illustrates the importance of delays in air blast generations as well as ground vibrations. There's very little discussion put into air blast delays or delays caused by air blast. But you need to be aware that is something you need to consider on occasion as well. Okay, but those are open air detonations. All that energy went into the atmosphere. Then the last example I have here of open air detonation, are you going to see, this is, I forget how many pounds of explosives, about 3,500, I think. They're making industrial diamonds here. Watch this pressure wave reflect up through here. So with open air detonations, you get very, very strong concussion waves that aren't always visible like that. Here, you're just far enough away and the light's just right that you see it refracted in the atmosphere, but you certainly will see that on the blasting seismographs. The acoustic channel very clearly picks up those events. So confinement is important for and how adverse effects are generated and or controlled. All right. So, what happens when we detonate a shot? It's like dropping a pebble in water. You displace the water near the impact, and then there's ripples that emanate out from that in a concentric fashion in both the ground and in the air. What I want you to do is look at this little diagram in the lower left-hand corner, and this is analogous to dropping a series of small pebbles in the water, one after another. Each time the pebble impacts the water, there's an individual wave that generates or radiates out from that point of impact, and they don't ever catch up with one another. All right. That's what we're ideally trying to do when we detonate one hole per delay. But over here on the right-hand side, note this Doppler effect. Say we're detonating a series of holes down the front face, and as you're detonating in one direction, the waves on one side are closer than the waves in the other. And sometimes they catch up with one another, depending on the sonic velocities of the rock. So it's something to be concerned with on occasion if you've got to control vibrations. And it's also important from an air blast standpoint. Okay, because these air blast waves can catch up with one another very easily, depending on how far apart the holes are spaced. So conceptually, I'm trying to get you thinking about how this energy radiates out away from the site, because it's important to know that so that you can adequately gauge what's going to happen in the field. All right. From a global perspective, okay, some of the larger shots, while normally we're dealing with smaller ones, some of the larger ones can be felt globally. This is a little graphic that was put together by the Arms Control and Disarmament Agency in the mid-1990s as they were negotiating nuclear test ban treaty. These are all seismic monitoring stations across the globe, and they daily pick up blasts, especially out of the Powder River Basin, large coal mining blasts, on a global network. And part of the effort was to differentiate the difference between these larger coal mine blasts and, say, small nuclear detonations. Can you tell the difference from a seismograph signature standpoint? You bet. Okay. But it's sort of a neat graphic to show that, you know, something like this can be picked up globally. I don't remember how many pounds of explosives this was, but probably 2 or 3 million pounds would be my guess. But that type of blast is felt globally. It's measured globally on the seismic network. So, you know, certainly those people living near mine sites are going to feel these activities, even for the smaller shots. In terms of vibration energy, it's good to have some idea of sonic velocities and acoustic velocities as well. On the ground, in bedrock, body waves are probably going to be about 20,000 feet a second, surface waves about 5,000 feet per second. The surface waves are going to be predominantly unconsolidated materials. And they will affect how the seismogram looks at the house. The air blast, traveling about 1,100 feet per second, okay? And it's going to arrive at some time later than the incoming ground vibrations. For all practical purposes, when this first hole goes off over here on the left, the energy is traveling so fast that at a house, say 2,000 feet away, at 20,000 feet per second, for all practical purposes, it arrives at instantaneously. But at 2,000 feet, this air blast takes about 2 seconds to get there. And you'll see that ground vibration arrive, and then later on, the seismic trace from blasting seismograph, the acoustic arrival. But these things help you address the adverse effects. Individual holes detonating, as long as they all detonate one at a time, surface delays working in conjunction with the downhole delays in this video. The charges go off independent of one another, and those energies never really couple together to create an elevated ground vibration level. So it's all about charge size and delay intervals as well. Okay, and this illustrates the blue circles, ground vibrations emanating out, and then a much slower air blast departure based on the orange or yellowish circles. Very common. Okay. Okay, now spatial relationships are important as well. You know, what we just saw were, you know, just radial energy emanating out from each blast hole. Well, it's going to be affected by superficial features as well, the spatial arrangement around. Here at the blast site, you have a high wall or a big pit between house 1 and the blast and house 2. In this particular instance, you would expect the ground vibration levels to be stronger in the direction of house 2 than even house 1, even though they're roughly equivalent in distance. But house 1 is probably going to see higher air blast. So those spatial relationships become important to consider as well. We measure all this energy that's radiating out a wave with the use of seismographs, okay? You've touched on this. The recordings are recorded or are controlled by how the units are made and how they're deployed in the field. You have no control over how they're made. That's covered by performance specifications, but how they're deployed in the field you have control over. And I'm pretty sure you've already covered that, so I'm not going to spend much time there. But what the seismographs do is they pick up what went on the ground. Here's a shot that started initiating at the far end, and it's tied to the detonation on the ground. And you're going to see when the shot gets right to this area, there's going to be 40 holes that sympathetically detonate, and you get this huge pulse in the seismogram here. What's important with having a seismograph, it helps you identify where something went wrong in the shot. It's an independent third-party piece of information that helps you go back and figure out, gee, why did we get an elevated ground vibration event? Why did we get an elevated air blast event? And if you get good enough in interpreting the seismograms, at least in a larger shot like this, gives you an idea which part of the event to look at. What went wrong? Who loaded that part of the shot? Who drilled that part of the shot? And then you can refine the overall process based on the seismic information and acoustic energy information that's been made available to you. This is a nice schematic of that same shot. I like the way that this will show you how the holes are detonating one at a time, about 3 million pounds of explosives. Look how the vibrations are being pushed a little bit stronger towards the viewpoint here, towards me, and they're moving off. It gives an idea how you can push vibrations and how they really do radiate out. There again, you're going to see 40 holes go pop right about now, boom. Yellow bus, you'll see this huge concentric ring generating out by virtue of them all detonating at the same time. It's what we're trying to avoid. It could be an issue with loading. It could be an issue of sympathetic detonation. Could be an issue of cap malfunction. Could be programming error. Okay, so, the control of the adverse effects isn't just in the design itself, but it's in the quality control of implementation in the field. All right. So, not only, there's 3 good reasons that we use seismographs. One's for compliance with the rules, which most people tend to focus on. But, it's a really important tool from a standpoint of evaluating blast performance. Because it helps us figure out which part of the shot we need to look at that was problematic. The third thing that it provides is liability protection for the blaster, okay, especially when it comes to property damage claims. All right, so that, I think, gives you a broad overview of some of the things you need to consider. Now, the next couple tables I'm going to throw up for you are out of the Blaster's Handbook, okay? And first off, we're going to talk about those things that are out of control of the blaster that challenge their ability to control the adverse effects. Number 1 is the surface terrain or topography. All benches aren't level. All rock units aren't planar or aren't flat necessarily. They could be steeply dipping. So, it becomes challenging not only, from a design standpoint, but from a drilling and field implementation standpoint. The rock type changes from site to site. Blaster has no control over that. They're simply asked to remove the rock mass for sale, or if it's the overburden for coal, they've got to get rid of it, or if it's maybe for a road cut. But the depth, the type of rock that they have there, it's not their choice. They've just got to pick the right equipment, drill the right holes, select the right explosives to get the job done. And that relates to the depth of the ore and or overburden as well. The blaster can take a 100-foot unit of rock he needs to break and say, break it down into 2 benches, 2 40-foot lifts. All right, you can work with that a little bit, but still he's going to have to get to grade. So it's not something he has much choice over, or she. And then weather conditions, which obviously are going to affect air pressures more so than anything. What are some of the things that the blaster does have in their control? This little chart gives a good idea of the things that they can significantly consider when controlling ground vibrations, and others that aren't so significant. What are the 3 primary ones? Charge weight per delay, delay interval. The charges need to go off far enough apart that energy doesn't couple together, and then create a larger wave, and then charge confinement down below. Those are the 3 items that are critical that the blaster needs to evaluate. Some of the things that are of moderate control, burden and spacing, certainly has a huge impact on confinement. You pull the burden in too much, lower it, and don't change the charge size, then there's going to be radical release of energy out front. Borehole accuracy, direction of initiation. A couple of the other things, like I said, from a direction of initiation standpoint, you can push the vibration stronger in one direction than the other, depending on that initiation sequence. Things that don't have much effect, the stemming amount, the stemming type, charge length and character, charge weight per blast, depth and detonating cord. Probably not many people using detonating cord at this point in time. In terms of design, things that the blaster can use to minimize adverse effects, certainly reduce the charge weight per delay, which is a primary design element. Can change explosive types. I'm not going to get into detail on these. You do have these in your book, and I would strongly recommend that you review them. But I think, based on what I've given you up until this point in time, hopefully they'll make a lot more sense. Initiation system selection. It's important to get the accuracy that's needed. Obviously, in more critical areas, electronic detonators in particular are going to be much more accurate than the pyrotechnical detonators of non-L or electric systems. They can modify their timing strategies. I know some blasters just give a mountain of effort in tinkering with different timings to get the best performance they can. And then lastly, just the overall design of how these things all come together. The field control, things that the blaster needs to pay close attention to: drilling accuracy, loading accuracy, confinement, and just overall quality control. A bad driller can make a really good blaster look bad because the confinement is all miss at that point in time. So that's for ground vibrations. For air blast, the strongest effect here is that it's out of control of the blaster. The weather conditions, if the weather conditions are adverse, their best course of action is to delay the event until some later point in time. But from an air blast standpoint, there's a lot more things that they have in their control that have a significant impact over air blast generation. Certainly when the stemming is released out the top, there's not enough stemming, or the stemming is of poor quality, the explosives energy is going to rifle at the top of the hole like shotgun and create an elevated air spike. That's probably the most significant issue. There are times where there's a huge amount of venting out the face because there's, say, a mud seam or some other geologic irregularity that intersects the borehole and the free face. And that's going to cause energy to be radically released. Design control issues, again, charge weight is another big indicator. Delay interval, there again, keep going back to that, and it focuses on getting those charges to detonate far enough apart so the energy doesn't couple together. And burden and spacing, lastly. For blast implementation, again, from an air blast standpoint, I strongly recommend that you go take a look at these. Drilling accuracy is probably the biggest one. If the holes aren't drilled straight or drilled at the angle they're supposed to be drilled, everything falls apart. All the other assumptions are null and void. You can very quickly end up with a mess on your hand, both from an acoustic standpoint and a seismology standpoint. Stemming, again, need to have enough stemming to confine the energy in the ground and indirectly prime the boreholes. All right. That covers ground vibrations, air blast, touching on fly rock. And we'll leave you with some nice examples here too. Anytime there's a radical release of energy, like on the left here or on the right, even though it's stemming, venting, and the arrow does point to a rock that's about to go into orbit, probably not, but they can be launched very, very far distances. In this particular photograph on the right beyond the disturbed area in the background, there's a creek in Pennsylvania. This mine went down there and picked up all the fishermen out of that creek because it was fishing season before they detonated the blast. because they need to have that area secure. So sometimes you need to go out and round people up. Just be aware of that. Okay, so what is fly rot? It's material ejected from the blast site that travels through the air or along the ground. Okay, that was set in for excuse me, set in motion by the force of the blast. From a regulatory standpoint, you can't go more than half the distance to the nearest dwelling or occupied structure. Can't go beyond the boundary of the protected blast area that's been defined by the blaster, nor can it go beyond the permit area. Those are the rules in effect for coal mining. So basically, it's prudent to keep your rocks and dirt and other things on the permit area. You know, if you don't, you know, you can damage things like trucks. Okay. Big piece of rock can do a significant amount of damage to a truck that's on site. They can cause fatalities. This was a Kentucky fatality a little over 10 years ago. Somebody got struck with a piece of rock about 1,800 feet away from the blast. And the rock bounced before it hit him too. It's still enough to cause a fatality. Fly water. This is an example of this truck that's down at the bottom was sitting here at this turn, blocking a shot that took place up on the hill. The shot swelled the wrong direction, went into a sediment pond and emptied the contents of this pond down this road, washed this truck up over the embankment here, and about 300 feet down through all these trees and ended up in a stream down below. 2 people walked away from that. It's unbelievable just looking at that. So, you know, not only is flying rock and debris important, you got to consider other things as well that's going to be impacted by your blast. Off permit, there was a fatality in Tennessee on Interstate 75. It wasn't a rock, it was a piece of mud that went through the windshield of a car and killed a person. So the problem there was explosive material was loaded into unconsolidated material. The blaster didn't talk with the driller, who should have told the blaster that there was unconsolidated material and you need to lessen the explosive column. Blaster ended up going to jail for this, 6 months. Okay, it was a criminal offense for a wide variety of reasons. I'm not going to get into those, but it illustrates the point of the importance of the blaster talking to the driller and getting the right information. There's more near misses than you can believe out there. Speaking of near misses, this is a hotel camera that had a fly rock event. Watch this lady walking right about here. She's going to walk right across the front of this shed. And right before she steps out from in front of that shed, watch right there. Boom. That was a piece of rock that was sent 1,600 feet from a quarry blast. Lots of near misses out there, but that's what an incoming rock looks like. Can create significant injury. And there again, that rock was set in force by virtue of the fact that something had vented out the free face. When you have a rock that travels that far, it comes out the free face at a low trajectory and can travel a very long distance. The rocks that come out of off the top of the shot, they pretty much go vertical and stay pretty close to the blast site. Those free face rocks are dangerous. And when they land off site, they can go into parking lots. They can land in farmers' fields. Farmer's not very happy when he runs his tractor into one of these things. All right, but that's a sizable chunk of rock as well. Sometimes rocks are set in motion in steep slope areas that they roll down over the hill. So if you've got rocks on an outslope in a steep slope area, they can be set in motion by the force of the blast. Got to consider that as well. Right there, you're looking at a $1.5 million rock for that trailer. It's ultimately what the settlement was. So it can be very expensive as well. This is an example of shallow holes, parting shot, okay, where a lot of the material goes vertical. And as long as the blaster's far enough away, probably not going to have a problem. But it certainly does create a large amount of air blast in this instance. Here's an example of a rock where they're conducting secondary blasting on this rock here. They've tied this rock in with a larger shot. The initial intent was to have this shot go off first, come out here and cover this rock so that there wasn't a likelihood of any flying rock from this secondary blast. Well, that material didn't get there in time. Watch this direction here. You see a vapor trail going off in that distance, and that rock went several hundred feet. So when you're conducting secondary blasting operations, you need to make sure that you adequately confine that material as well. Here's a misfire. What happened here is the first half of the shot went off, and they hurried back in and retied the part that got cut off into the shot. Then consider the loss of confinement on this front face. And when it detonates, it sent rock 2,500 feet down over the hill into somebody's house and backyard. Here's what that looks like. There again, that's a field implementation thing. Be careful with misfires. This was a road cut where they didn't adequately couple they bore tracked the holes on this site. They face profiled. The blaster didn't bother to take the time to look at that data once it was compiled, tied together, to see that he had some weak spaces or spots in the high wall. And this is what happened. Had a huge amount of venting from right here, went across a 4-lane road, went across a 4-lane road, went across a railroad track, and went halfway into the Allegheny River outside of Pittsburgh. About 1,300 feet total. The blaster here lost his license for 6 months. If you're going to take the time to bore track the holes, make sure the holes are in the right place, and face profile, take the time to digest the data so that you can load the holes properly. All right, this is a face example where these two arrows are. You're going to see one rock hit the face, the corner or lip of the high wall here, and this one's going to clear this high wall. This rock here went over 2,500 feet. You'll see vapor trails from them, basically. One just barely nicked right there, and there were 2 vapor trails venturing in that direction. All the result of weak spots in the high wall that are really hard to identify on occasion. Here is an example of stemming that blows out, throws rock 300 feet down over the hill. Okay, so the first thing the blaster wants to know in that situation, as a general rule, who loaded that hole? Somebody overloaded a hole, created an elevated air blast, and threw rock 300 feet down over the hill into somebody's house. So quality control is essential. So with that, in your notes, you're going to see that there's a number of causes of fly rock. I think I touched on most of these at this point in time. I'll leave them there for your reference. In terms of, again, I think I touched on all these. Okay, but they're simply listed for your future use. When it comes to preventative measures, the simple ones, the appropriate powder factor for the rock type at hand, okay, again, it's a confinement issue. Appropriate primer placement, most often in the bottom of the hole, so the holes don't thin out the top. Make sure that the lays are adequate so that holes in rows in front of the back rows, they all detonate and begin to move out before subsequent rows detonate. You know, that rock response time is important. If you're in tight conditions, try to avoid making the pattern too deep. Too many rows leads into over confinement in the back rows, and the material tends to go vertical. Stem through in composite zones. There again, that's where the blaster needs to be talking to the driller to make sure they've covered the weak zones and have the holes drilled appropriately. Make sure the blaster needs to make sure the crew is loading the holes the way they are supposed to be loaded in the blast design. If there's too many, if there's a number of decks, the decks need to be loaded properly. Stemming material and communication between the driller and the blaster. So with that, we'll just leave you with the primary ones. You know, charge weight per delay and the distance are the ones you normally focus on most of the time, but you got to keep an eye on confinement as well in terms of blast design. And then once it's designed right, you got to implement it right in the field and pay attention to all the details. I said I'd mention just a little bit about fumes. There's a picture of a really significant cloud. And no blaster that I know of would walk into that cloud. It would be very hazardous to your health. Secure an area that's large enough so that you, anybody else you're working with, or anybody offsite is not exposed to those types of events. So with that, hopefully you have a better idea, and I'll take any questions if you have some.
Thank you, Ken, for your interesting presentation. I think I missed we are running out of time, but I missed one point on the misfire shot. I don't know what you mentioned about a couple of slides. If you go back, the misfire.
Yeah.
Yeah, so what was the issue here?
Okay, what happened is they detonated a shot, and the front half of the shot detonated, and the back half did not. I think somebody forgot to tie in one connection.
Okay.
So, you know, they hurriedly went back in and retied in and conducted a second shot that wasn't adequately confined.
Got it. Okay, cool. So do you guys have any questions for Ken? So, all right. So thank you again for taking the time to speak to us today. We really appreciate it. It was very interesting presentation. Thank you.
Good. I appreciate the opportunity and look forward to doing it again sometime.
Sounds good. Thank you, Ken. And I'm going to end the session here today and stop recording.
Okay.
So you have a nice day, Ken.
Good luck.
Yeah. Bye.